Good. Thank you very much, Jérôme, for the introduction. And first, I would like to thank the committee for the very kind invitation. It's a great pleasure for me to be here and share with you some recent development on computational tools for mostly mixed matrix membrane. Then, as it was already discussed by the speakers this morning, then here, when we have the membrane separation, we know that the membrane separation processes are very energy effective technology compared to other adsorptive separation or cryogenic separation. And then when you see the literature, actually polymeric membrane dominates the market. Then the problem of the polymeric membrane is that they show mostly two limitations. The first one is a trade-off limit between productivity and efficiency. Then what we call the Robson upper bounds between selectivity and permeability. Then there is a limitation. And the second point is that most of the polymers, they show what we call plasticification. Then it means that it is associated with the swelling of the polymer when you use a high pressure gas, high pressure condition under working condition. And then you see this swelling behavior, and there is a dramatic drop of the permeability at high pressure. Then it means that you need to find alternative to polymeric membrane. And here the idea was first, then I show you one example on a pure MOF membrane. Then it is the platform that was initially introduced by Osama in his talk, the FCU topology. Then here in this case, the idea was to fine-tune the pore entrance of this platform just to make an irregular shape of the entrance by making a mixed linker strategy with fumaric and megasaconic. And here the idea is to finally block the accessibility of CH4 versus nitrogen. Then it is what we call a shape mismatch for methane compared to nitrogen, because here with the spherical molecule, you see clearly a mismatch of the molecule towards the triangular windows, while for nitrogen, you have still a free diffusion pathway. And here we have done some DFT calculation for the different configurations, and first starting with a pure fumarate linker and increasing the concentration of mesaconic in the ring. Here you see you have 3 linkers in the windows. Then you can increase from 1, 2, and 3. And what is interesting is that when you introduce one mesaconic, which is a methyl fumarate, then you see a drastic increase of the energy barrier for methane to cross, while for nitrogen, the increase is less pronounced. Then in that case, you are suspecting that you are favoring the diffusion of CH4 versus nitrogen. And here is a beautiful work that has been done by Cheng and Osama to prepare the corresponding membrane. And here you see in this graph that for a ratio 1:2, then here you have 1 mesaconic and 2 fumarate, then you get a high selectivity of nitrogen over CH4. And when you look about this graph, reporting the selectivity as a function of the permeability, you see clearly that this material outperforms both the polymeric and inorganic membrane. Then it was recently published in this paper with also collaboration with Jorge Gascon and also group from Edaudi. Then actually another alternative solution is to go now for a mixed matrix membrane. And here the idea is to combine the best of the two worlds. Then of course you want to keep the selectivity of the MOF and as well as the processability of the polymer and the chemical stability, etc. Then here the point is that you can see in the literature a few candidates that has been reported, but most of the time, the choice of the pairs have been done in a way that finally, without really understanding the microstructure of the composite, and as well as understanding of the mechanism in play to explain their separation performance. And in particular, the problem of MOF polymer interface is a key for two main reasons. The first one, it controls the adhesion between the two components. And then, of course, you need a good compatibility between the two components to get a very homogeneous dispersion of the MOF in the polymeric membrane. And then, of course, it means that you will make a very continuous macroscopic membrane. And second point is that this interface is the first entrance towards the MOF filler. You need to make sure you have a very effective diffusion pathway for the gas. Then here the idea is to combine modeling in tandem with experiment to try to engineer the MOF polymer interface and further design a very advanced MMM. Then here is the platform we have been developing over the few years, starting with a first step where we can construct different MOF surface based on the DFT calculation. Here, for instance, you have an example with a Z-fate. We start with a bulk Z-fate. We can cleave different surface slab model, and then after we can optimize and then also play with the nature of the terminal groups of the surface. From the other side, we can make in silico polymerization, starting with different monomers and creating the polymers you want to play with. Once you have the two sides, then you bring the two models together, and you can make equilibrium molecular dynamics simulation using a force field to optimize your system and to get the more polymer composite. And from here, you can already understand what is the interface between the two components and in terms of interaction, in terms of polymer coverage, etc. And once you have done this analysis, if you find, for instance, a good compatibility between the two components, you can go to make a membrane setup. And in that case, you use non-equilibrium molecular dynamics to explore the permeability of the gas towards the composite. And our first step was to apply and validate our approach with different MMMs, mostly in terms of compatibility. Then here is a few articles we have published with different groups in this field. And once we have done this, then I will show you what we have done in a systematic way to improve the quality of the MMM with different collaborators. Then here, for instance, the first idea we had was to explore in a systematic way the role of the polymer flexibility, rigidity on the compatibility between the MOF and the polymer. And here we started with the model MOF, UIU66, and we screen different polymers or different mechanical properties. And here we worked with polymeric of intrinsic microporosity, PIM1, polystyrene, PVDF, and PEG, with the idea to change the flexibility of the polymer. Then, for instance, here we can classify the rigid polymer, like with a very rigid backbone for the PIM1 and polystyrene as well. And then in that case, we can see that when you associate the polymer with the MOF surface of UIU66, you create some microvoids. Here about 15 Armstrong, here about 8 Armstrong. When you go with a flexible polymer, then you have a very nice coverage of the surface of the UIU66. Then here with PVDF, with PEG, you see clearly that all the surfaces of the MOF are nicely covered by the polymer. And when you look about this radial distribution function that characterize the interaction between the MOF and the polymer, you see clearly that the coverage is controlled by hydrogen bond here, about 2 Armstrong and 1.7 Armstrong, between the OH group of the MOF surface and different functions of the polymer. Then here, I show you still an example with PDF and PEG that in some cases we can even have some polymer infiltration into the MOF. Then is a work we have done in tandem with Seth Cohen in San Diego. Then here you see clearly that in PEG case, you see clearly the polymer can even penetrate the entrance of the UIO66 and going towards the cage. Of course, after, when you have this computational data, you want some validation. And here, Seth was able to make the corresponding membrane with a very continuous film with a very nice dispersion of the MOF filler in the polymer matrix. Here, we have the same case was UIO66 PIM1, where we found a very bad compatibility between the MOF and the polymer. And then it is a work that has been done also with Osama. Then here you see, based on the SEM images of the corresponding composite, as well as the high resolution TM, that you have some micro voids between the MOF nanoparticle and the polymer, and the dispersion is very poor. Then it was a way to validate also our simulation. Then the idea was to see how, in the case of the UIO66 PIM1, we can improve the compatibility between the two components. And the first criteria we wanted to change was to make a polymer functionalization. Then here, computationally, we screen different functions that can substitute the cyano group of the PIM1 with the idea to see how the compatibility will be controlled by the functionalization of the PIM1. Then in the case, for instance, on a functionalization with a long tail chain, then you see that you can improve the compatibility between the PIM1 and the UIO66 by a partial penetration of the pocket in the UIO66. Then you are expecting a better adhesion between the MOF and the polymer. When you look, for instance, on the other functions and with the amidoxime function, which is here, represented here, you see that you can have another criteria to improve the compatibility by creating strong hydrogen bond at the surface. And here you see, here, for instance, a very large overlap, because here you have the atomic density profile of both polymer and MOF, and here you see an overlap between the MOF and the polymer. Then it means that you are expecting a higher degree of adhesion between the MOF and the polymer. Based on this, again, with a very nice collaboration with Osama in cows, here they were able to make the functionalization, and clearly when you see these two different pictures on the SEM images, you see that you improve the dispersion of the MOF in the polymer. And here, you don't have any more this macro void at the surface of the polymer, at the surface of the MOF, sorry. Then it means that you are expecting with this to improve the compatibility. But the problem, when you look with, when you work with polymer functionalization, you have a very big drop of permeability. Then for application, it's not so great. Then we need to move to another strategy to improve the compatibility between the PIM1 and the MOF surface. And the other strategy, as it was already discussed before, is to try to make, to engineer MOF surface defects in the UIO66. Then here, it is what is represented in this scheme. Then we wanted to create either missing linker or missing cluster at the MOF surface and combine with this defective MOF with the PIM1. And here is the result we found. Then here we have the initial pristine UIO66 without defects in our model, with an overlap region above 5 angstrom. When we include some defects at the MOF surface, then you see clearly that you have an increase of the overlap between the MOF and the polymer, because then you have some pockets that you can see here. Polymer gets inside, and in that case, you increase the overlap. And what is also interesting is that you can also look in this graph, you have the non-defective one in green and the defective one in orange. Then here is a polymer dynamics. Then here we follow the dihedral angle distribution of the PIM1, and you see clearly that you have two peaks in the non-defective one. In that case, you have a relatively large flexibility of the polymer at the MOF surface. When you create defect, you limit the dynamics of the polymer. Then it is also helpful to address the issue of the plastification. Then it is another, I would say, it is another positive point, compatibility, and also addressing one other trouble. Then here, after this, we want to understand what's going on for the permeability of the different gases in this defective system. And here, we plotted the mean resistance time using non-equilibrium molecular dynamics for CO2, slender molecule, CO2, N2, and the spherical methane. And here you see that in the case of here you have the same color codes, and defect is in the blue-green, and here is the orange. Then here you see that at the interface where we are interested to work with, then the resistance time for CO2 and nitrogen here is increased compared to the non-defective one, while CH4 is similar. Then you can expect an increase of the transport, acceleration of the transport following this order, CO2 faster than nitrogen and faster than CH4. And then, of course, it is of interest also for the selectivity if you consider CO2 over CH4 or CO2 over nitrogen. Then here after, we didn't have a direct proof on UIO66 PIM1 defect, but we moved to another system. Then here, still the platform zirconium fumarate FCU, then a work that has been done also by Cheng and Osama. Then here you see that they were able to prepare a defective MMM with including some defects in the zirconium FCU. Then here you have, they obtain a very nice homogeneous membrane with a I would say, with a very good dispersion of the MOF in the polymer matrix. And here, what is good also, that when they made tests to test the stability of the MMM in THF, you see clearly that for the defective one, you also increase the stability of the MMM compared to what they call low defective MMM. Here you see that experimentally, when they made the permeability experiments, then here in that case, they observed an increase of the permeability by a factor of 2 between the non-defective or low defective system towards the high defective system. And interestingly, the selectivity remains more or less similar, about 20 here at 10 bar, for instance. And interestingly, compared to this, you see that the selectivity performance is maintained over pressure for the defective system, while for the non-defective one, there is a significant drop. Then it is also consistent with the fact that you address the plastification issue and the drop of permeability at high pressure. Okay, just. Okay, then here, our non-equilibrium molecular dynamics simulation, we're interested to understand the diffusion of CO2 and nitrogen in this system. And what we have found is that in this graph, we report the selectivity of CO2 CH4 versus the CO2 permeability. We have an increase about 1.5, factor of 1.5 for the permeability, while the selectivity is relatively even improved in the case of the defective polymer. Another aspect we want also to try is trying to promote what we call orientated 1D channel MOF polymer to improve the compatibility between the MOF and the polymer, but also the performance. And for this, we came back to a platform that we were exploring in the past with aluminum F5 here made of the square grid and where you have the pillared aluminum F5. And here the interest of this material is to have a kind of molecular sieving effect of CH4 over CO2. And here we use this platform because in that case, we can orientate the surface along the channel direction. Then it means that we can expect to have a very nice coverage of the surface by the polymer. And in the meantime, we wanted to have some preferential pathway for the gas towards the full MMM. Then here again, we constructed the surface model for the aluminum 5. Then we worked with the polyamide 6-FDN-DAM polymer. We constructed our composite. Here you have a top view of the composite we were able to construct. Here you see that the polymer is covering part, I would say, all the part of the MOF surface, forming some interconnected voids about 3.5 angstrom. And what is interesting is that this size allows CO2 to get in. Then please run the animation. Okay, good. Then here in this animation, in this movie, you see clearly that we can define some pathway from the polymer side to the MOF material where CO2 can pass. And here, when you look about the side view, where you see the interface created with this composite, you have a corridor section which is maintained by a continuous interaction, van der Waals interaction between the MOF and the polymer. And what is interesting is that in this corridor section, you have interconnected pores about 2.5 to 4 angstrom. And then in that case, you limit the CO2 to spread over this direction, which is also good for the global permeability because you want the gas to go directly from the polymer to the entrance of the MOF pore. You don't want the CO2 to spend a lot of time in this region and to lose some productivity of your MMM. Then here again, we explore the CO2 permeability towards the MMM. What we found is, in the case of the polymer region, we had a purely Fickian diffusion regime. Okay, then it means that the mean square displacement follows a linear trend with the time. Then in that case, both in the polymer and the interface model, we can extract the diffusivity. And interestingly, in the MOF, once the CO2 gets inside the MOF, then we have what we call the single file diffusion regimes. And it means that the molecules are not crossing each other. They are diffusing behind each other because finally here the channel is very confined, then about 3.5 to 3.6 angstroms. And it means that you are really a regular diffusion of the molecule towards the MOF. And you see that the diffusion remains more or less flat along the MOF direction. And based on this, again, nice collaboration with the group of Professor Edaoudi, Shuvo Data prepared a nanosheet of MOF. Then here you have the MOF nanosheet. These nanosheets were able to be nicely dispersed in the polymer matrix. Then here you have the very nice dispersion of the nanosheet, and particularly the orientation was very well controlled. Then here you see that the molecule can go through the polymer and through the MOF. And in this graph, you see the performance of the CO2 CH4 selectivity for different polymers, and not only 6-FDN-DAM, but also DAT and DAM-DAT. Then here you see that with this system, it's possible to achieve selectivity more than 150 with a relatively good permeability for CO2. And it was also shown that this membrane can be very effective for not only CO2 CH4, but also in the presence of H2S. Then it is a paper that has been published recently in Science, where they demonstrated finally the rational design of this MMM for molecular separation. Okay, then now, based on this platform of aluminum MF5 6FDM DAM, then the point is that, as I mentioned before, okay, then here with the 6FDM DAM, we had a flat profile for the diffusion along the MOF, and the permeability was not, I would say, exceptional. We had a very high selectivity, CO2CH4, but permeability was about 1,000 barrier. Then it means that we can still improve the performance in terms of permeability. And here the idea was to be inspired from the bio field, because we know that molecular sieving and ultra small pore MOF are not only acting in MMM or separation processes, but here, for instance, if you look about the aquaporine, which is a protein channel, this protein channel, which is very highly selective for water over ions in a cell membrane, this aquaporine shows this kind of corridor section. Then here you have the conical shape, where you start with a very inner small pore, and then after you have a large pore in contact with bulk water. Then here the idea is to try to mimic this kind of environment to allow a smooth transition from the polymer to the entrance of the MOF to improve the transport of the gas towards the polymer, from the polymer to the MOF. Then here, what we try to do, then here, you remember that I show you the corridor section, which was not really, I would say, perfect to allow the molecule to align along the MOF entrance. Then here the idea was to screen a different polymer to scaffold the same environment that we have in the aquaporine. And then we found one polymer that allows this kind of vestibular shape at the pore entrance. And here, I show you what we have done after in terms of transport of CO2 with the molecular dynamic simulation. Here, what we found is that in the case of 6FDM DAM, the MMM I showed you before, compared to this, the residence time for, I would say, the concentration of CO2 at the interface is lower compared to the one in the 6FDM DAM, because we want to avoid accumulation of CO2 at the interface. Then here you see that this objective is achieved. When you look about the residence time, it goes in the same trend. For 6FDM DAM aluminum MF5, you have a residence time about 600 picoseconds. Here, in the case of, 600 nanosecond. Here, in the case of the polymer we found with this vestibular shape, you have a decrease about to go to 400. Then it means that we are achieving the goal we want to have less CO2 accumulating in the interface. Sorry. And then again, after we try to analyze the diffusivity, then it goes in the same trends. And here we have an acceleration of the diffusivity in the other polymer we found compared to 6FDM DAM. And interestingly, we are not only able to accelerate the transport at the interface, but we have also a propagation of the acceleration towards the MOF. Then here you see the data I showed you before with the flat profile with the 6FDM DAM. Then here you have a flat profile for the diffusion towards the MOF, along the MOF channel. Here, interestingly, we have an increase of the transport. Then it means that we have a kind of cooperative propagation of the acceleration at the interface, which is made possible because in the MOF channel, it is so confined that finally the single file diffusion allows you to have an acceleration towards the MOF channel. And here we are expecting now some experimental work to validate these findings. Then just to conclude, then here the idea of this talk was to tell that finally we really need to understand what's going on at the MOF polymer interface. We need to really have this fundamental understanding to guide the experimental work towards a more elaborated MMM. Then here with 4 direction, polymer functionalization, with improvement of the adhesion, but permeability drop, we can edit or we can tune MOF surface defects to achieve also both improvement of adhesion and also improvement in terms of performance. We found this strategy very useful to make MMM with exceptional gas separation performance for natural gas treatment. And here we go with this new idea with the use of vestibular shape to improve both permeability and also adhesion. Then to conclude, I would like to thank my group and particularly the MOF gamers, then who did very good and very hard work on this topic. Our exceptional collaborators for the preparation of the membrane, then particularly Shubo, Cheng, and Osama for all the work I have shown before. Funding from KAUST. Again, thanks so much for the Dresden team for the very nice organization and very nice program. And if you are interested to join the group, I have some PhD and postdoc positions, and please, you are free to contact me. And thank you again for your attention.
So yeah, thank you very much, Guillaume, for this very amazing talk and show how competitions would help accelerating discovery of breakthrough systems. So that's crazy. So is there any question from the audience about this computational work and the discovery of new systems?
Okay. No, I want to have a question after you. I'm quite interested in the PM simulation. So what kind of simulation method do you use, DFT or just dynamics?
You mean for the construction of the PIM1 model, you mean?
Yeah. PIM1.
Yeah, is it just, in that case, it's just force field calculation, okay, where you make an in silico polymerization, but you just rely on the charges that you can extract by DFT. But everything related to the construction of the polymer model is based on force field calculation.
How many polymer chains have you included in the simulation?
Yeah, then it's a good question. Then for the PIM1, we worked with a different type of chains. Then it means that we had polymers based on a dispersion of small chain, about 10 to 20 monomers. And also we created a long chain of PIM1, more than 120 monomers. And then we compare the influence of the size of the polymer on our calculation. And then the idea is to validate these two models with density that can be obtained experimentally. And then we were just making some feedback to validate our microscopic model in this way.
Okay, are the pristine polymers, have you included a small portion of solvents like chloroform or DCM?
In this story, not, because it's an automatic way to create the polymer. Then you define some generic criteria where you create the association of more of the monomers together. But we have also developed another strategy where we are including the impact of the solvent like chloroform, etc., to make some other polymers. Then we have the two approaches. The first one is using a polymatic software that has been developed in the US by Colina. And the other one, where we include the impact of solvent, then we have developed our own software that can be applied for many different polymers.
Okay, thank you.
Thank you. Yeah, we have one question from the chat from Fernando Uribe Romo. Can you mention the difficulties on simulating mixed linker MOFs?
Okay, then here's the point. Okay, I can comment it directly. Then here in that case, we we use the regular distribution of the linker, mixed linker. Then, because we wanted to understand what is the role of changing the fraction of fumarate over mesaconate to see how it impacts the entrance of the gas. Then we were not really interested to know how the linkers are really distributed in the periodic structure. Then here it was just focusing on the pore entrance.
Okay, thank you. There any other questions? I will give you mine.
Thank you, Guillaume. Very impressive talk. I have a question. How do you decide on the termination of the MOF surface? Because you showed how important it is.
Yes.
And what is the, how you decide how it's in reality, actually?
Yeah, sure. It's a good question. It depends finally the solvent you use when you make the MMM. Then most of the time the first step is to consider that we have dissociation of water, because as a simple model, we consider that it is done in water. Then it means that in that case, we consider water and we saturate the dangling bonds by OH and H as a surface. This is the first step. But if we want to improve the quality of the model, we can coordinate the terminal growth by chloroform or whatever type of solvent. And then experimentally, for instance, in the case of the aluminum 5 story, they tested different solvent to prepare the MMM. And then we are in a way to terminate in a different way the MOF surface to see how it impacts the compatibility first, but as well as the performance. Then it's quite flexible for our side to change the termination depending on the solvent you use experimentally.
So thank you very much, Guillaume, again for the brain talk. And I think we can thank together all the speakers of this session. Thank you.